Hello, welcome to Noise Control and its Management. Today is the third day of the ongoing week, which is the 7th week of this course, and starting today we will start moving in a different direction, and over the next 2 weeks we will learn techniques through which we will be able to figure out roughly the sound pressure level at a point of interest due to the presence of different types of machineries. Now, these machineries could be present either outside in a field, or they could be present inside closed rooms. So, what is our problem? The basic problem which we are trying to address is noise estimation. Noise estimation. So, what does that mean? Suppose you have a closed room and you have all sorts of sources of noise. So, this is source 1, source 2, source 3, source 4, source 5, all these machines. Each of these machines is producing noise, and I have a person here, and we want to know what is the pressure level, at this location. So, we have different machines, and we know the distance between this source, and this is a closed room. We know all the details of the room, how it looks like, what kind of shape it has, what kind of materials it is made up of, and we also know what these machines are, what kind of motors they have, what kind of gears they have, do they have a fan, do they have pump, all this thing, and based on all that we will try to calculate the noise level at this location. Okay. So, this could be either inside a room, or it could be also if there is no room and we are just outside, let us say on a football field, and on a football field we put a genset and some pump for making pumping out water from the ground, and we are interested in figuring out what is the noise at this location. So, noise estimation, that is our goal. Now, before we start discussing how do we come to these estimates, we have to learn one important concept, because it will come very frequently when we are doing noise estimation, and that concept is of directivity. So, broadly we have already discussed directivity, what it means, but now we will try to give a mathematical definition for directivity. So, what does directivity mean? So, if you have a point source, it emits sound uniformly with equal intensity in all the directions. So, this is a point source. It is a point source, and if I at a distance r, if I measure this distance r using this angle theta. So, at a distance r, if I plot the polar pattern, so this is theta equals 0 degrees, this is 90 degrees, this is 180 degrees, and this is 270 degrees, and at a distance r, if I plot the sound pressure level. So, I can measure the sound pressure level at this location or this location, like this, at different locations, but the r remains same. Then what I will find is that it is just a regular circle whose center lies at this origin. So, what this means is that so the so for this radius, so let us say r is equal to 10 meters. So, for r is equal to 10 meters, the amount of decibels which is expressed in terms of the distance from the origin, it is same. So, it is a, so this is an omnidirectional source. This is an omnidirectional source, but you can have a different type of source. Suppose you have a source which is a horn, a horn. It is not a point source. What will the directivity of this be like? It will be the sound, you would expect that the sound is going to be stronger in this direction and it will be weaker in this direction, it will be stronger in this direction and it will be probably very small in this direction. Okay. So, if I make a directivity plot for this, it may look something like this, and this is just a very crude. So, this horn, so this is a horn, this is highly directional. So, different types of sources could be either omnidirectional or they could be directional sources. And what we want to do is, now we want to quantify, because later, I mean, we want to quantify how this directionality can be mathematically expressed. So, that is what we will discuss. So, there are three ways to quantify directionality. So, the first definition of directionality or quantification is through this term called beam width. Beam width. So, what does this mean? So, suppose you have a horn, so you are blowing into it and it is producing this sound. You will have louder sound in this direction and lesser sound in this direction and maybe very small sound on the back in the negative direction. So, suppose this is our origin. Okay. So, what is this horn doing? It is essentially throwing a beam of sound, because the sound is not spreading uniformly in all the direction. So, for instance, you have a beam of light. Light is more intense inside the beam, and then if you move away from the beam, the intensity of the light is less. So, similarly, sound in this case, as produced by a horn, it is in a sort of a beam, it is a beam of sound, and we try to figure out how wide this beam is, So, so this is what is meant by beam width, okay, and we will make a more precise definition. So, suppose, so what is, so we will first define it. So, beam width is the value of angle with respect to 0° direction over which sound pressure level falls by 6 decibels, So, this is actually known as quarter power width. And we will explain all this. Quarter power width. Here, usually 0° direction is the direction of maximum intensity. So again, let us say there is a horn, this is the horn and this is my x axis. So this is the origin, origin. So this is my origin and this is my x axis. Now when I blow the horn, we would expect that the sound is going to be maximum in this direction, right. If you are right in line of the horn, you will hear the loudest sound. If you are away, then the sound is going to. So suppose you are 10 meters away from the horn, it could be anything, 10 meters, 5 meters, whatever. And 0 degree direction is the, so that is what it means. 0 degree direction is the direction of maximum intensity. So first we have to figure out what is our 0 degree direction. So this is the 0 degree direction. So in context of horn, it is along the line of the center of the horn, that is the 0 degree direction. There the sound will be at the maximum level. Now let us say this is, so this corresponds to, let us say 100 dB. Then I keep on measuring for different values of theta. Okay. So let us say this is 20 degrees, this is 10, 20, 30, 40, 10, 20, 30, 40, okay. These are different values of theta. And here what I find is that in the 10 degree direction it is 99 decibels. In the at 20 degree angle it is 98 decibels. At 30 degree angle it is 95 decibels. It could be anything. And at 40 degree angle it is 94 decibels. So this is 94 dB, this is 95, this is 96, this is 99 and so on and so forth. So this is 40 degrees. And similarly, it may be symmetric around 0 degree axis or it may not be, it depends on the source, but in case of horn it will be symmetric. So this is again 94 dB at 40 degree angle. So what does that mean? That if I go away from 0 degree and the 40 by 40 degrees, the decibel value falls from 100 to 94. And on this other side also, when I move by 40 degrees, decibel value falls by 6 decibels. The radius does not change, the distance from the origin does not change, the radius has to remain constant. Then I will say that beam width and which type of beam width? Quarter power bandwidth. Quarter power width is equal to 80 degrees, or I can also say plus minus 40 degrees in this case, 80 degrees or plus minus 40 degrees, because the power level has gone down by 6 decibels. Now why do I call it quarter power? I call it quarter power because when I go down by a factor of half, that corresponds to 3 decibels. Okay. And when so this is half power, and when I go down by a factor of 1/4, it is 3 plus 3, so it is 6 decibels, that is 1/4 power. So the beam width, if I am using this quarter power standard, is defined when the pressure falls by 6 decibels. Similarly, there is half power bandwidth, and in case of half power bandwidth, it is the amount of theta you have to go from the 0 degree axis when the power falls by 3 decibels. Okay. So that is the beam width. So this is the first way to measure directivity of a source. A source which is extremely directional, it will have higher bandwidth or lesser bandwidth, not bandwidth, it will have more beam width or lesser beam width. It will be lesser beam width, it will be very sharp, right. So, sources which are very sharp, they are they have very thin beam width. Omnidirectional, in case of omnidirectional it does not make sense, but you can, because you do 360 degrees and it still does not fall, right. But as a source becomes more and more omnidirectional, this beam width, it increases. As a source becomes more and more directional, its beam width becomes more pointed and more sharp. So, this is the first measure of directivity. The second measure of directivity is directivity factor. Okay, by the way, before we talk about directivity factor, beam width, it can change from one frequency to other frequency. For instance, a source could be pretty much omnidirectional at very low frequencies, okay, especially if its size is very small compared to the wavelength, but at high frequencies maybe it becomes more and more directional. So, beam width, let us call this BW, is a function of frequency, it changes from one frequency to other. So, maybe it will have a 40 degree beam width for 2000 hertz, but for 5000 hertz maybe the beam width could be only 10 degrees, it could be that. Okay. So, it is important to understand that whenever we are talking about directionality or directivity, it is very strongly dependent on the frequency of interest. So, directivity is often also expressed as Q, and again Q is a function of frequency, and this is defined as the ratio of I divided by I ref, and we will explain what this means. So, suppose there is a source located at this point x, okay. Let us say it is an ideal source, it is an ideal source and it produces, so it is a point source monopole, and because it is a monopole it produces what kind of waves? Spherically symmetric waves. So, this source, an ideal source, is omnidirectional, it is omnidirectional, and let us say, so it is an ideal source and it is producing n watts of sound energy. So, each second it generates n joules of sound, and all this sound spreads equally and uniformly in all the directions. Okay. So, that is my reference source. So, this is my reference source. Okay. Now, so this is my source, I will call it S, and I am interested in finding out directivity factor. Okay. So, my microphone is here at a far away point and I am interested in finding out the directivity factor. Okay. Now, what do I do? So, QF is called directivity factor, it is measured by I and I ref. So, if it is a point source, if it is a point source, then it will be omnidirectional, right? It will be omnidirectional. Now, suppose I have a machine or a small sound producing object. So, I want to find out, so I want to find out the directivity of a real sound source. So, let us call that S2. and let us designate it something like this, some complicated shape S2. So, this reference source is S1. So, what do we do? What we do is, first I put my microphone at the desired location, and at the place where S2 is going to be located, at the same location I first put an ideal source, and I measure the sound intensity at this using this microphone. So, that gives me I ref, that gives me I ref. So, you understand? So, I put an ideal source which is omnidirectional, and at this microphone location I find out the pressure, and using mathematics, mathematical formulae, I can calculate I ref easily. And then what I do is I replace S1 by S2. So, in the second step I replace S1 by S2, and then what happens? The sound does not spread uniformly in all the directions. So, again I find the value of I, and I calculate the ratio, and I calculate, and then that is how I figure out the value of directivity. Okay. Now, this directivity will change, it will change. So, this may be 0 degree direction, this may be some other theta, and so it will change. So, directivity QF will change with theta, it will change with theta. But normally we assign 0 degree direction to that orientation when what? I is maximum. Normally we do that. Okay. When I is maximum, then we assign that direction as 0 degree direction, and we usually measure directivity in such 0 degree direction. So, what does that mean? That if a sound source is omnidirectional, then what will be the value of directivity? It will be 1. It will be 1, because I, intensity of the omnidirectional source, because and of this real source, it will be the same. Oh, by the way, this real sound source should also produce same power level, n watts. Okay. So, the total watts is the same. So, if I have in the if the actual source S2 is omnidirectional, then my Q will be 1. If the source is not omnidirectional, but it is directional, then Q will be more than 1 or less than 1? It will be more than 1, because in the 0 degree direction I have the direction for maximum intensity, and that will be always more than the intensity produced by an omnidirectional source. Okay. So, because of this, because of such a definition, QF is always more than 1. So, always more than 1. So, this is directivity. Once again, Q depends on frequency, it is a function of frequency. And the third parameter is directivity index. So, that is di. Di equals 10 log 10 of QF. So, that is directivity index. Okay. So, these are the three ways to measure directivity. One is through beam width, second one is through directivity factor, and if I just take the log of directivity factor and multiply it by 10, I get a directivity index. Okay. So, for an omnidirectional source, what is the value of directivity index? For an omnidirectional source, directivity index will be 0 and directivity will be 1. Okay. For a directional source, directivity will be more than 1 and directivity index will be non-zero. So, this because it is more than 1, what does that mean? If it is more than 1, then directivity index will be what? Log of 1 is 0, log of anything more than 1 is a positive number, right? It is a positive number. So, directivity index will be a non-zero number and it will be also positive, it will be a positive number. Okay. So, that concludes our discussion on directivity, and starting next class we will start discussing the basic problem which we have talked about. So, or actually we will do one more concept as to how sound gets absorbed in air. So, that is the other thing we would like to learn, and then we will start discussing about our basic problem, which is what we had described earlier. This is the problem which we will try to address. So, that concludes our discussion, and I look forward to seeing you tomorrow. Till then, have a great day. Bye.